Okay, I think we'll try and make a start. How's the sound up the back? Audible? Okay, thank you. So we're trying a couple of, I'm trying an experiment tonight. I'm recording the screen of the presentation, and the plan is to post the video to YouTube sometime, probably tomorrow, so that people who aren't able to make the class can still watch the lecture. So that's a bit of an experiment. If there's background noise, they won't be able to hear. It's a bit of an experiment, so we'll see how that goes. Like last week, I'm going to risk Slido again. So there's a different number this week. So make sure if you use Slido, you log in with 7166 is the number for questions this week. So again, I'll check the browser every now and then and see what questions pop up. I appreciated someone tried to rickroll last. Oh dear. All right, so the tone has been well and truly established, so we'll see where we go with this. Last week, you hopefully recall, I introduced processing, and we worked on doing some basic drawing with sort of predefined shapes. So we worked on sticking up a rectangle on the screen, sticking a triangle on the screen, sticking an ellipse. In the lab, you worked on putting those things together to make a house or a cat and stuff like this. This week we're following on from that and doing some more advanced drawing. So this is just drawing with stuff other than predetermined shapes, in other words. Let me check and see if the tone's improved just in the last 30 seconds. The question about hardware is a good one. Can we create our own hardware for the projects, like using Arduino or similar? And if so, would all group members need to create separate hardware prototypes? The short answer to that is this is not a hardware subject. So unless you can convince your tutor that hardware would be worthwhile for your group and that your group is on top of all the software stuff well and truly, then the default answer will be no to that question. But if you're interested in that sort of stuff, there is a new subject called Prototyping Physical Interaction that Sam Ferguson is running, and I think it's running next semester for the first time, but I'd have to check that. But if you're interested in Arduino and stuff, there's a whole subject that's going to be devoted to it, so maybe save your energy for that subject if you're interested in hardware stuff. If you are okay with hardware, is it okay to throw it in? I'm still going to say by default no, because I don't want to end up with a situation where you have a group where one person's on top of the hardware and the software, and 3 other people are kind of going, I don't know what's going on. But we're open to negotiation, so you can present a really convincing argument to your tutors. We will listen. We won't just say no blanket up front. But it will be hard to convince us. Okay, so moving on. The pre-reading for this week. Are you all getting the emails from UTS Online that kind of outline what you need to be doing prior to class each week? Yes? Yeah? So if you're not, you need to make sure you're forwarding your UTS email to some address that you actually read. Because each week I'll send an announcement out saying you should be looking at this chapter or this video or this whatever material it is. And if you're not getting that stuff, you're going to be struggling. So the pre-reading for this week was chapter 3. Don't forget the book is available through the UTS library website, so you don't have to buy a hard copy. Hopefully you've all found how to access it on the library website. That's where it is. Each week I will also try and present interactive doodad of the week. It could be an interactive artwork. It'll hopefully be something which is sort of relevant to the assignment without being a solution to the assignment. So this week's one is by Golden Levin, who is a digital artist, I guess you would call him, who's done a lot of interesting interactive work over a number of years. And if you check out, if you Google his name and search his website, he has a lot of good videos documenting lots of interesting projects that he's done. And this particular one is called The Dumpster, and I'll play you the video. So this is a kind of interactive visualization and a kind of sonification as well. Just make sure that volume is reasonably high.
Developed in time for Valentine's Day, The Dumpster is an interactive visualization of romantic behavior on a grand scale. Using real postings extracted from millions of online blogs, visitors to the project can surf through tens of thousands of specific romantic relationships in which one person has dumped another. The Dumpster presents a collection of 20,000 romantic breakups that were blogged during 2005. Entries mentioning the phrases broke up or dumped me were first harvested and then carefully filtered for reliability and accuracy. The project's graphical tools help reveal some of the similarities, differences, and underlying patterns of these failed relationships, providing both analytic and intimate perspectives onto global romantic pain. In one part of the interface, breakups are each represented by a small bubble. The interface allows the visitor to surf the collection of breakups by skipping from one breakup to others which are similar, as indicated by their color. As a result, visitors to the Dumpster can experience both the unique stories of specific individuals, as well as observe a group portrait of a blocking generation.
Okay, so a few years old, that one, but you get the idea that they've gone and found a whole lot of blog postings in which people have mentioned breaking up with someone, and they've gone and harvested those blog postings and put them into this interface where you can navigate and compare and contrast all these different breakups. So yeah, it's just an example of one kind of interactive visualization. Not so much a sonification, that one, there wasn't much sound involved, but it gives you an idea of it might stimulate you to think about one kind of idea that you might implement for your assignment where you're looking at either the US election or the Building 11 data. Okay, are there any questions about the assignment before I go on, either verbally or on Slido? Oh, great, Slido's killed the interaction, great. Okay. So, moving along, back to processing. So I'm assuming most of you who have kind of got some experience with programming would know what a function is. And you would know that in Java, a function or a method is just a way of giving a name to a block of code that you want to reuse. So we can define a function called draw squiggle. We give it a name. We put some code in between the curly braces here, and then we can invoke that method or that function. We can run it by just calling it by name in our code somewhere else. So a quick example, and I'm not going to labor this point unless people are freaking out about it, but I'm assuming you're kind of on top of it. How readable is that? Is that okay at the back? Yes? Okay. Thank you. Let me just comment out this bit to make it a bit simpler. And that bit. So here we have a method, draw squiggle. I'm using the normal Java syntax, so I'm saying that it's a void method. In other words, this method doesn't return any value. I can write other kind of functions or methods which maybe do a calculation and then return some number or some string to another part of the program, but in this case, this is just a block of code that does something. So I've declared it, I've given it a name, draw squiggle, and then in the block of code between the two curly braces, I've stuck some code here which draws a squiggle on the screen. So we'll actually be looking at this code later on, and you would have hopefully read about it in chapter 3 anyway. But we don't need to worry about the details. It's just a block of code that draws a squiggle. And when I want to call that method, when I want to actually draw a squiggle in my code in some other place, I simply use the name of the method. That causes processing to jump down, execute this block of code down here, and then carry on. And it's convenient because I might, in my program, want to draw a lot of squiggles in a lot of different places in my program. And rather than cutting and pasting this code into 50 different places in my program, I can simply invoke that code just by writing draw squiggle, and we're done. Yep.
Is it, if it was following sequentially, is it code finish that whole function then continue?
Yeah, so if it's following sequentially, does it pause, finish that function, and then carry on to the following lines of code down here? Yes, it does. So the execution will kind of go this line, this line, this line, this line, oh, draw squiggle, jump down to here, do all these lines one after another, then return back and do whatever lines follow afterwards.
Doesn't it get laggy and stuff? If, like, for example, that function is really big?
Yeah, if it potentially could get laggy, if you've got that function and it does a lot of really complicated stuff, and maybe it's opening a connection to the internet and doing a whole lot of stuff, then while it's doing that, the rest of the program is not executing. So you need to be a bit aware of what you're doing, I suppose. Yeah. But for something like this, the impact on performance would be negligible. Yep. If we want to run the second program.
Second program to the previous one.
If you want to run, you mean the second program? You mean this one is the second program?
Yeah, if we want to run first this and then the first one.
Yep.
But we have
Okay. Well, I'm about to get to explaining what the setup method does. But the setup method is automatically called by processing as the very first thing that happens when your sketch runs. Okay, so what you could do, if you want to draw a squiggle to run the very first thing, you could drag that line of code and stick it up here, and then it would be the very first thing that executed when your program ran.
in any program, it will take setup firstly.
Yes.
It is the priority of this.
Yeah, and that's a very good leading to the next slide. So in any program and processing, the very first thing that happens is the setup function or setup method will run. Yep. So let me just quickly run this to sort of show you what it actually does. And there we go, it drew a squiggle. And if I run it again, I think it draws a slightly different squiggle because it uses random numbers to vary things a little bit. So, and with your functions as well, as those of you that are familiar with Java would know, you can also have functions which take parameters. So let's say that I want to write a draw squiggle function, which, and I want to be able to specify how wide the line is, how wide the squiggle is that it draws. In that case, I can say, yeah, this method, this function, takes a special parameter, which I'm going to call line width, and this will set the width of the squiggle that I draw in this method. So it's exactly the same as the previous draw squiggle, except this one takes an extra parameter called line width, which I use to set the width of the squiggle that I'm going to draw. So if I uncomment this, we should now see that there is two squiggles drawn. The first one is calling our standard draw squiggle method with no parameter here. The second time we call draw squiggle and we pass in 10 as a parameter. So that's going to call in the second draw squiggle down here, which takes the line width as a parameter. That will then set the width of the line to be drawn and draw a squiggle in a similar way. So if I run this, we should see two separate squiggles, one with a thick line and one with a thinner one. And you can see that's what's happening. And again, if I run it again, we should see slightly different combinations of squiggles. Okay. Are there any questions about the basic concept of functions and how they work? So if you're freaking out, That's okay. It's not great, but it's okay. Well, one sec, let me just finish this point because I started it. If you're freaking out and you really don't understand functions and you don't have much familiarity with programming at all, that's okay. Help is at hand. If you look at Daniel Schiffman's series of videos, he has a series of videos specifically on functions and how they work, going into a lot of depth about it. So I'm assuming most of you are kind of going, yeah, done it, boring. But for those of you that it is new to, check out these videos, and Daniel explains it very, very well and in great depth. Did you have a question?
Can we go
Yep.
what's the stroke weight?
Stroke weight. Yeah, so I didn't really explain that. Stroke weight sets the width of the pen that you're drawing with, to put it simply.
The tree or the line width, like it, and the weight of the first line is the narrow to the second one.
Yes.
So the stroke weight set this width.
Yes, it's just like picking up a different width texture when you're drawing. So there's a default stroke width, and I'm not sure what it is, but that's what the first one would use. And the second one, you set it with that parameter. Okay, so... Okay, so now I mentioned before that there is a setup function, and you saw an example of that in the sketch I just showed. That's the very first thing that processing runs when it starts up a sketch. So that's a good spot to put, to say set the size of the output window, maybe to set the background color of the screen, stuff like that. Things that need to happen only once when the program first runs, you stick them in setup.
It's the same like the void main in Java.
It's the same as void main in Java. Yeah, kind of. Yeah. Just think of it as being the very first thing that happens when processing runs. Now the second method you're going to be using a lot, the second one which is kind of built into the framework of processing, is the draw method. And this runs every single time processing outputs to the screen. So processing outputs to the screen by default 60 times a second. So if you're doing animations and things like that, you need to keep redrawing to the screen to make your animations work. So by default, processing will do that 60 times a second. That means that the draw method is called 60 times a second. So if you want to make your sketches interactive, or you want to make your drawings that you've made move around, you'll need to use draw. Okay. So I'll give you a simple example of how that works. And by the way, while I think of it, you should know all the example code that I'm using here. So if you look on the slide, you'll see example draw demo down here. And then on UTS Online, there's a zip file that contains all the examples for this week, actually plus a bunch more as well. And you can sort of cross-reference there. So when you look at the slide and you see draw demo in the example, that's referencing a sketch in the examples I've uploaded to UTS Online. So if any of this stuff goes by too fast, you can download it and check it out. And a lot of the examples come from a book. Okay, so draw demo. So we've got two methods. First one, setup. As you know, that runs the first time the sketch starts. So that just sets the size of the screen, too easy. Then we've got our draw method. So this runs 60 times a second. And what happens here is we set the background to be black. And then, well, what's this doing? Anyone want to have a stab? Yeah, exactly. It's going to make a rectangle of size 100 by 100 where the mouse is. So again, mouse X and mouse Y, those variables are built into processing, and processing automatically updates them. As the mouse moves around, it'll update them to reflect the current position of the mouse. So again, they're very useful things that you're probably going to use a fair bit when you're doing processing sketches. So if we run this, let's just check that it actually works. And you can see now, whoa, we have interaction. 60 frames a second of interactive goodness. And what's So that's pretty awesome in itself. You could already put that on the App Store and sell it for $1,000. But what's going to make the difference is if you take out the redrawing the background, then it gets even more awesome, because then it goes all weird. So now it's drawing the rectangle every time you move the mouse, but it's not clearing the background. So we're just getting rectangle on top of rectangle on top of rectangle on top of rectangle, which actually I think looks much more interesting than the first version, which didn't have a bug. So something to keep in mind. Okay, any questions about that? About setup and draw? Yep. Oh, just one sec. I had to hit his hand up. Yep. Will doing that thing in the background eventually overload the memory? No, I don't think it actually will. Yeah, but I'd have to try it. I've never tried running it for longer than a few seconds. I don't think so. Thinking about the way graphics cards work, I think it probably doesn't actually matter. Yeah. Sorry, you had it.
Mouse X and mouse Y is previously defined function for this activity.
Mouse X and mouse Y are previously defined variables, yep, that contain the X coordinate of the mouse and the Y coordinate of the mouse. And you don't need to declare them to use them. Normally, if you want to use a variable in processing, you have to declare it. But in this case, you don't have to. You just use it, and processing has already made it for you. It's just there. You can just use it. Just like setup and draw functions are kind of automatically invoked. There's some magic that's happening under the hood you don't really need to worry about. It just does it. Yeah. Okay, so that's draw. Okay, so far, except in draw squiggle method, we've used predefined shapes. So we've used rectangle, like rect method to draw a rectangle, and we use triangle and ellipse and point. But you're probably going to want to draw more sophisticated shapes or more complicated shapes that aren't necessarily made up of squares and triangles and rectangles and stuff. And if you want to do that, you use vertices in processing. So you can think of a vertex, when you're using vertices, you can think of it like a big dot-to-dot drawing that probably many of you sort of did. Maybe you still do them, I don't know, but maybe you did them when you were a kid, where you have the drawing like this, where you kind of join a straight line from point 1 to point 2, and then from point 2 to point 3, and point 3 to point 4, and so on until at the end of that process you've drawn something. Yeah, so in this case you would have drawn a cat. And vertices in processing are pretty much exactly the same principle. You use the vertex method to essentially place a dot of your dot-to-dot drawing at a certain point on the screen. So you might say vertex 100, 100. That puts a dot on the screen at 100 pixels across, 100 pixels down. Then you might put another dot at 150, 200, and then another one at 200, 320, and then another one, and another one, another one, another one, another one, wherever you want them. And then after you've put as many vertices on the screen as you want in your dot-to-dot drawing, you use this end-shape method and pass in close, and that tells it, draw a straight line between all the points we've just plotted. Yeah, so wherever you put those dots, it'll then connect them all up one by one in the order that you plotted them. Does that make sense? Yep, so if I'll show you an example of how to do that. So this is pretty much from the book. So I've got two methods in my sketch here. The first one is called setup. So that runs the first time the sketch runs, as you know. We set the size of the screen, we set the background to be white, and then we call this plot rect method and pass in 4 numbers. And the plot rect method is one that we've written down here. So who's read the book or who can tell me what this does? It makes a rectangle. Yep. Can someone explain how it makes a rectangle and why it works? Yep.
Vertex, and each subsequent vertex is basically being connected, like the connected dots and at the end, and then it's the shape. Go find the rectangle.
Yep. Yeah, exactly. So it plots vertices at each point of a rectangle, and then by calling the N-shape method with the closed thingamajigger in it, it joins up those dots to make the rectangle. And if you look at the parameters that are being passed in, the first point is at x and y. The second point is x, y plus the height of the rectangle. So if x is up here, that's our first point. Sorry, x and y. Our first point's up here. The second one, we have the same point in the x coordinate, but plus the height of the rectangle, so that will be down here. Third point is x plus the width of the rectangle and y plus the height of the rectangle, so that's over here. And then the final one, x plus the width and y, which is back up here again. So if you can kind of think that through, you can kind of imagine we have 4 points, and then join them all up, and we get a rectangle. So let's check it out. So we're passing in 100, 100, so that should be the top left corner, and 400, 400, that should be the width and the height. So it more or less is a square. Not more or less, it's exactly a square. Let's run it. And there it is. Anyone know what it would do if I took out, oh, not that. Sorry. Where's my sketch gone? No. Can anyone tell me what it would do if I took out that?
Maybe it wouldn't connect the last line with the first area.
Good guess. Yeah, you're right. So that passing in that close word tells processing to connect the last dot to the first one, which is often what you want if you're drawing an enclosed shape. If you don't want that, don't use close. Are there any questions about that before we move on?
We not use the N-shape method.
Yep.
In the last. So what happened? Is this running again and again?
It's a very good question. What happens if we don't use the N-shape method? Anyone want to have a guess? Or has anyone tried it? If we don't have N-shape, if I just take that out?
Is this run again and again?
But your guess is it'll just run again and again. Anyone else have any other guesses? Nothing? Yep. So you think it will never actually draw the shape? I think you're probably right, but I could be wrong. Yeah. So without N shape, nothing happens. So if you're running your sketch and getting a blank screen of death, maybe it's because you left out that N shape. Yeah. All right, let's press on unless there's any other.
So it's necessary to give the end close.
If you want to see something, yes. Yeah. Often you want kind of controlled randomness in your sketches. I mean, randomness can be a very bad thing if it's completely random, but controlled randomness can be a nice way to get variation in the graphics that you're showing. Maybe you want random colors to kind of make the screen look a bit more interesting. There's a nice built-in random method that does that for you. So we can say, if you want to generate a random number between 0 and 4, you could call random method like this. If you want to generate a random number between an upper limit and a lower limit, you pass in 2 numbers. So fairly straightforward, I hope. So with that in mind, let me have a quick check of, what's her name? Good question. Can we use other software for our projects? No. You can use processing and you can use pure data, which is what we get to in a few weeks' time, which is for audio, and that's it. Yeah. Because I've had in the past where I said, yeah, you can use other software, and people have gone off and picked something ridiculously complicated piece of software and spent all semester getting lost on that piece of software and not delivered anything and had all kinds of pain. So I'm saying processing and pure data are a very powerful combination. You can do a lot with those, and we're going to insist you stick to it. If there is some add-on bit of software maybe that you could use as well to just make some task a little bit easier, talk to us and that should be okay. But in general, processing and PD are it. Yep.
What if you wanted to generate a random double?
A random double? Very good question. I'm not even sure what the actual difference technically between a double and a float is in processing, or if there is one.
Wait, so because I don't know if does that random generate like every single possible value or just integers?
That one's generating, that one returns a float.
Oh, so it can be like 2.45.
It'll be 2.453 or something like that. But you can cast it to an integer, I think. But yeah. So, yes, anyway, where was I? I was here. So, randomness. Not here. So you guys figured out what the last sketch did. Maybe take a minute if you to talk to your neighbours. 1 minute to have a quick talk to your neighbours, and then see if you can explain what this does and why. And then I'll pick on someone to tell me. So what it does is probably fairly self-explanatory just from reading the name of it. But if you can explain to me what it actually does down here, that's a bit more complicated. So take a minute, have a quick chat with people if you would like to or need to. Okay, so I think I can hear you've kind of been throwing some ideas around there. Would anyone like to have a crack at explaining what it does? First up, it's relatively easy to figure out what it does, I think. Anyone?
It draws a four-sided shape points that are not necessarily rectangles.
Yep, it draws a four-sided shape where the points are not which is not necessarily strictly rectangular. Yep, yeah, I think you pretty much got it. Can anyone have another stab at what it does, or explain how it works?
Creates a rectangle where each corner is shifted by a random number which has the range of whatever you cross it.
Yeah, it creates a rectangle where it shifts each corner by a sort of a random amount based on what value you pass into it. Yeah, so you're both you're right. So your answer is pretty much on the money. So let's just work through it. We've got all these parameters being passed in. We've got x and y, w and h, so width and height of our rectangle. But then we've got float rand w and rand h. So I would think of this as a randomization factor width, randomization factor height. Would be a better name for that variable, but they've tried to be concise. Okay. And I'll show you a nice cool feature of processing that you might find handy as well while we figure this out. So what I'm going to do is put a breakpoint here. I think. Oh, there. First I'll enable the debugger. Then I will click here, and if you see where I clicked on that line, this little diamond showed up. That means when I push the start button on processing, it's going to run, but as soon as it gets to that line, it's going to freeze. And then we can use this little window over here to look at the value of the variables that we're playing with. So let's, I'll start running it. Nothing comes up yet because the processing sketch is just frozen at this line. So we've set the size of the screen, we've set the background, and now we've called this method and we're frozen right on this line. And you can see that the x parameter is 200, y is 200, width is 200, height is 200, randomization factor for the width is 0.2, and randomization factor for the height is also 0.2. That's a bit hard to see probably, but I'll zoom in as much as I can. So now I'll execute the next line of code by doing step and step. So now we've initialized jitter W and jitter width and jitter height. So that has been calculated as the width of the rectangle times the randomization factor for the width. So randomization factor was 0.2. So now the jitter for width is 200 times 0.2, which is 40. And then I did exactly the same thing for the height. So we've got jitter width, jitter height is now set to be 40. So this is going to be the amount that the points, the corners of the rectangle are going to kind of move around. But they're going to move around by an amount around based on 40. So we're on the next line of code, begin shape. So we know what that does. That starts drawing a dot-to-dot drawing with our vertex commands. Then we place a vertex at x plus some random number between minus 40, which is jitter width. Remember that from over here, minus 40 to plus 40. So the first point, the first x coordinate for our first point is whatever the x coordinate is that we passed in, plus a random number between minus 40 and plus 40. And y is exactly the same thing. So whatever our y coordinate is also going to be varied some amount by some random amount between minus 40 and plus 40. And then we do exactly the same thing for each subsequent point. So every point of the rectangle that is being set just as we did in the previous sketch, but this time we're just moving it around a bit with some randomness. So each point is going to be kind of moved a little bit from where it would normally have been. Does that make sense? Yep. I think so. And then after we've plotted all those 4 points, we end the shape and close it. So what we hopefully end up with is kind of a squarish looking thing, but with some randomness involved. Oh, and I need to run it. I need to turn off the breakpoint so we don't keep on freezing here. That's done. So there we go. So we run it, and now we get a kind of a rectangle with some variation. If I run it again, it's varied in a different way. So each time we run it, it's generating different random numbers for us, which means that the amount that the corners of the rectangle are being varied is changing. So each time we get a different shape. Yep. Is that all okay so far? Any questions? No. Okay, so randomness is very handy when you're doing games and, well, all kinds of things. Okay, so now probably the trickiest part of chapter 3 is where we start messing around with creating polygons. So the goal, what we're aiming for now, is to create a little function which can draw any polygon. So a polygon is just a multi-sided shape. So a square is a polygon with 4 sides. Triangle is a polygon with 3 sides. What's a 5 again? Pentagon is 5-sided, etc., etc., etc. So what we want to do is we want to create a method like this, a function like this. It's called draw polygon. We want to be able to pass in the number of sides we want. So it could be anything from 2 sides, 3 sides, up to 50 sides or higher. And we want to say what the radius of that polygon is. In other words, what's the width of it from the center to the outside point. Does that make sense? That's our goal? Good. I'm not sure if that oh my god was for this, having given you flashbacks to year 8. It does give me flashbacks to year 8. So luckily we don't really need to go into this a great deal. But you might, if you remember, year 8 was not that long ago for a lot of you, it was a lot long ago for me. So if you remember from year 8, if you have a right angled triangle and it has an angle in it like this, then there is this special kind of value called sine value, which is equal to the ratio of the opposite side divided by the hypotenuse. Yeah? So sine is opposite divided by hypotenuse. Cosine of this angle is the adjacent divided by the hypotenuse. And the tangent of that angle is the opposite over the adjacent. Okay. So, okay, big deal. Just store that away for a sec and remember it. Why is that of any interest at all? It comes in very handy when you're drawing shapes around a central point in graphics, which is something you have to do surprisingly often. So you can imagine if we want to draw a circle around, on the screen around the point 0, 0, one way to sort of conceive of that, one way to do it, is to plot a pixel, plot a dot, every 1 degree at a fixed distance from that point 0, 0. Yeah? So let's say I want it to be 200 pixels radius circle. I would plot a point at 0 degrees angle to the horizontal here, 200 points from the center. Then I'd plot a point 1 degree angle over here, 200 points from the center. Then 3 degrees, 4 degrees, 5 degrees, until I got to 360 degrees. I put a dot 200 pixels from the center at all the way around that circle. I would then have drawn a circle on the screen. Does that make sense? Yeah, kind of. I mean, the other way to do it would just be to kind of figure out, well, what's the x and y coordinate of this? Then have x plus 1 or x minus 1 and then y, and try and put it to a point that way. But it's actually a much more intuitive way, a much kind of more efficient way to do it if you plot a point at a fixed distance from the center, changing that angle all the way around. So I wrote a little processing sketch to do just what I said. So I'm drawing a circle what I'm calling the low-tech way, even though it might seem a bit high-tech. So I'm declaring a variable to be the radius. So this is the radius of our circle, the distance from the center of the circle to the outside in pixels. It's 200 pixels from the center to the outside. Set the size of our output window to be 800 pixels by 600 pixels. Then I begin drawing a shape, like we've done previously. Then I've done a magic line of code, which hopefully most of you know about, but some of you may not, which is just essentially going to count from 0 to 360 for us automatically. Yeah, so we're going to count from 0 to 360. The first time we get in here, this angle variable will be 0. And we're saying the x-coordinate is the radius the cosine radius times the cosine of the angle that we're creating. Oh, and I forgot a very important thing to say. Did you want to correct me, or were you going to say?
I'm just asking, I was just wondering, because some cosines and sines will become negative, so won't the circle be kind of out of it?
It works. I need to go back to something first. I forgot a very important point earlier on this slide here. So, using your year 8 maths, and we're not going to do it because it's not that important. You have to kind of, you can do the maths in your own time if you want to go back and enjoy those year 8 memories. But the whole thing about this, knowing about cosine and that sine, for example, is the length of this opposite side divided by the length of the hypotenuse, it allows you to figure out the x-coordinate at a point, a fixed distance from the center on a line that's a particular angle from the x-axis. And the formula is the x-coordinate of this point is the radius, the distance from the center, times the cosine of the angle, and the y-coordinate is the radius times the sine of the angle. Okay, and if you want to do some maths, you can do it. We can do it in the lab if you're interested. Ask your tutor; they can show you how you calculate that. But that's just an interesting feature of year 8 maths. It helps you figure out how to draw shapes around a 0, 0 point in the middle of the screen. Okay, and that's what we've done in this code. So we're starting off, angle is 0. We're calculating our x-coordinate using that formula. We calculate our y-coordinate using the same formula. Ignore this for now, I'll explain it later. And then we're plotting a point at those x and y coordinates we just figured out. And then we go back and we do exactly the same thing for when the angle equals 1. So when the angle equals 1, figure out x and y coordinates, plot them on the screen, go back, angle equals 2, until we've counted all the way to 360. So we're hopefully going all the way around the circle, plotting a point at a distance of 200 from the center, and increasing the angle from the x-axis by 1 degree each time. And then at the end, we end shape and close. So when I run, it works. So I could have done that with one line of code, and that would have been more efficient. But this way, hopefully, you've kind of started to get a sense of, okay, we can start to draw shapes around a center point using this sort of formula that we've calculated from year 8 maths. Yeah. And are there any questions about that before I press on? Yep. Oh yeah, good point. So the question was, how come when I go back in this loop every single time it lets me reinitialize x and y? The answer is because once you get to this end brace, x and y would actually be flagged as not needed anymore. So that would be taken off the stack, and then sort of each time you leave the block of code, those variables will be gone. Yeah. So yeah, a bit of a technical question, but a fair one. Oh, whoops, draw circle, draw circle. So the question is, what do we need to change to draw a triangle instead? Yeah, increment the angle by 60 degrees instead of by 1. Yeah, exactly. So at the moment I'm drawing a point every 1 degree, which is giving us a circle. If I draw it every 60 degrees, will it give us a triangle? Let's try it. So we just go angle plus equals 60. So that little line of code is adding 60 to the angle instead of 1 every time we come around the loop. So we're starting off at 0, do this. We come back next time, angle is then 60, do the calculation, plot the point. Next time it's 120, etc., until we get to 360. Okay, so you're on the right track, but you didn't quite do your maths right. So how many we got 1, 2, 3, 4, 5, 6 points here. So if you try 120 instead, that should give us a three-sided shape. Yes. Yeah. So the center point is here. We've plotted a point at 0, 0, with 0 degrees angle, 200 pixels from the center. Then we've plotted a point 120 degrees angle from this horizontal line, 200 pixels from the center, and then another one 240 degrees, and then we've closed the shape. Yep. Does it make sense? Yep. So, draw polygon. So what you'll see in the example code, and maybe I'm running out of time to really go into it, and there's probably more important things to do, is now that you've figured out that little algorithm, you can write a method which will generate a shape with whatever number of sides you like. So I've now got a method here which is draw polygon, and we're passing in the number of sides we want and how big we want it to be from the center to the outside of the shape. And then all we're doing here is saying exactly the same as before, except we're figuring out that, okay, well, if we want to figure out how much we have to increase the angle by every time we want to draw a new point, it's just a number, it's 360 degrees divided by the number of sides we want. So if you think about it, a triangle was 120 degrees, so that was 360 divided by 3, because the triangle has 3 sides. A square would be 360 divided by 4, whatever that is, and et cetera, et cetera. Yep. So in this case, I will quickly run the code. We can now, I'm drawing a polygon with 5 sides to start with. And if I make it 10, we get 10-sided shape, and so on. If I do 100, you'll get something that probably looks like a circle, because the shapes, the sides are so small you can't really see them. But you've used a very common algorithm to draw around a center point, which turns out to be quite a handy thing in graphics and processing, which is why I've kind of laboured the point a little bit. What if it is 0? 0 sides? Yeah, it's always good. It's always good to try these ridiculous parameters and see what happens. It's gonna, who can predict what will happen?
A point.
A point is a good guess. Someone else said divide by 0. I think you're right, because the problem is probably going to be here it's going to try and calculate 360 divided by 0, which is going to cause the computer to flame. So nothing happened, and it's saying division by 0 error. Yeah. If you make it 1, I'm not sure what happens then. Ah. Yeah. Oh, you guys are getting super geeky on this. 3.5 sides. Oh, there we go. Yeah, it doesn't work because I've said it's an integer, so you can't have numbers which have a decimal point. Okay, but good question though. Okay, last thing I'm going to talk about, because actually, I'm going to have to finish this. I think we're out of time because we've got another class coming in. So I will continue this lecture and record the screencast and post it to UTS Online. Just talking about transformations and how to move things around the screen, which is quite important, but I will post that tomorrow.